Hello, my name is Colin Lynch. I'm an independent researcher uh, developing a new branch of science called Temporal Sciences. This branch science is based on time, the study of time, and is the central theme for this branch of science. This could be a new branch of science that helps us break through some of the issues that we currently have uh, in front of us, and could be a different way to solve problems or a different way to approach problems. And I'm really excited about it. So, with that said, these ideas are speculative, they are unreviewed, not peer reviewed, and not seen by anyone. So please do not consider these as truth or fact or substantiated. These are simply brain dumps from me to you and ideas for sharing with the goal that we start conversations because I'm finding some interesting things and definitely want to share those out broadly. For example, today's topic with the Hubble tension. I've got an interesting perspective on that from the temporal point of view. So I want to share that out. Uh, this video is associated with the Foundations 3 section. So I already have Foundations 1 out there. That's defining time. Foundations 2 is the universal framework or universe framework. And Foundations 3 touches on gravity and space-time curvature. So I put this one out early before 2 and 3 because this theory and application exercise I thought was timely based on a lot of the discussion going on around the Hubble tension. Um, so let's see here. After this video, Foundations 2, the universe framework will be coming out probably in about a week or so. And then Foundations 3 with gravity and space-time curvature come out in a week or two. And with that said, if you were interested in reading ahead uh, from a one-to-one perspective, the documents are in the links in the description below. And uh, you can read ahead, and the foundation videos are based on those documents. So Foundations 2 is the universe framework document in the link below, and Foundations 3 would be gravity and space-time curvature, again in the links below. And for today's discussion, for the Hubble tension, that document is also in the link below and contains a lot of the information, most all of it, that you'll see in the slides presented here today. So, very exciting. Let's see here. Yes, all the PDFs are free and freely available, and PDF format, common format, posted on zenodo.org, and no cost. You can download those without any cost and in the common format. Housekeeping items from the first video. I'm going to say less. I'm going to try. And the highlighter did not record, even though I could see it on my end during Foundations 1. PowerPoint Live won't pick those up. So I don't have a good option currently. So I will be directing visually on a slide, just verbally going forward. With that said, let's just get started. Here it is again. I usually lead with this, or will be leading with this, the temporal equation, the foundation of temporal sciences. In all its glory, T equals D square root M over square root E. And that is foundational to temporal sciences. Can it change in form? Certainly. Will it change in form? Quite possibly. But right now, that's what I've started with. And I've made some interesting progress off of that equation. And so again, I just lead with these videos with the temporal equation since it is central to temporal sciences. For today's work effort or discussion, we're going to discuss the Hubble tension the varying values, the Hubble constant values, H0 meaning representing what the Hubble constant should be right now to represent the expansion of our universe. And then the Hubble constant overall, HT, at any given point in time, T, would represent the rate of expansion for the universe at that time. That's today's work. This work will demonstrate that the Hubble constant is not a fixed number or a specific number to be discovered through reverse engineering or analysis of our current environment, but it is actually a value that's intrinsically tied to the rate of change of time within the universe. That value, the current Hubble value, establishes the current value of the Hubble constant is necessary to match the present rate of temporal change while ensuring the gravitational constant remains invariant. All right, I messed that up a little bit. But to clarify, the Hubble constant has to be a fixed number at all times, not an invariant number, but fixed from the perspective of proportion to satisfy our gravitational constant. So we're going to get into that, and we're going to unpack that. And therefore, the gravitational constant itself, we will solve for the Hubble constant. At this point in time, we'll solve for HO, and we'll come up with an equation that'll satisfy HT. Okay, fantastic. We'll move on. Okay. I postulate that since the gravitational constant for a universe is defined by the rate at which time changes, then the Hubble constant value must always represent that rate in proportion to the diameter of the observable universe. I briefly touched on that before we arrived at this slide. This helps iron it out a little bit more. But that document in the link further below for gravity and space-time curvature, that's where it's explicitly stated, and that's where we replace gravity with a form of the temporal equation relative to rate of change of time. So by extension, we're able to work through and satisfy the Hubble constant. And then we'll continue on. Like the core postulates in my other documents, we're just going to simply state the postulate that we're going to work on. And then instead of unpacking it immediately, we're just going to start working. Here we have t equals d square root m over square root e. We started along with that. And in order to get the Hubble constant value, we need to establish time, the rate at which time changes, and the gravitational constant. We'll move to the next slide. So with respect to distance, we have a partial differential here for the rate of change of time. To the very top, square root m over square root e with respect to the change of distance. Now, there's 3 partial derivatives in the total differential, but for today, we're just going to focus on the one for change in distance. So as we move down this page, we interpret dt per unit of measured time. We use Hubble's law for recession speed. We'll pop in HO so we can get the value right now because we're going to use the current estimated diameter of the universe for d. So that'll correlate to HO. We arrive at dt over dt equals square root m over square root e, HO, d. Then we can substitute in square root m, square root e, and replace that with 1 over c. So for the right-hand side, we have Hubble, HO, d over c for our rate of change of actual time. And remember, t is actual time, and then clock time. Clocks only measure the rate at which time changes. And for further clarification on that, that's the first document in Foundations 1, where we define time. Clock time, or measured time, measures the rate at which time changes, which is the derivative of actual time, which is the integral of clock time. So therefore, actual time is the cumulative area under the curve, cumulative sum total of clock time, and clock time is the rate at which time changes. And so we use both of those as a tool to unpack things, no differently than we're going to here. So previous work, the rate at which time changes for a universe, this is the gravity and space-time document. This is where we replaced gravitational constant with the temporal replacement. We did that for the Newtonian physics, and we did that for space-time curvature and the field equations. So in terms of temporal sciences, G is gone. The word that shall never be spoken, because gravity, from a temporal perspective, does not exist. It is an output of the change of time. It's not its own force. Gravity doesn't exist. It's simply an evidence of the change of time. So that's covered in Foundations 1 and the time and distance document. Foundations 3, the gravity and space-time curvature document in the link below. So we'll reread. The rate at which time changes for a universe, dt, or clock time, or measured time, is the definition of the gravitational constant, G, for that universe. And so we see here what I just spoke about that's in the gravity and space-time document. G equals HO d over c times the scaling factor. The scaling factor is mentioned just below, 1 times 10 to the negative 11. No other numbers. We're just simply driving the decimal point back. M to the third kilograms, -1 seconds to the -2. So that's a scaling factor to mate our output, our numeric output, with the gravitational constant. Again, we're mating the rate and change in time with the gravitational constant. So we need that decimal point to change and the units to be added back in. Now, it could be argued, well, your math is a little fuzzy if you're driving decimal points back and forth and scaling and everything like that. But this is all very new. It's all very new. There's very many edges for discovery here. The central point here is that when we get to the 6.67430, that when that number matches, whether it's a mantissa or matches decimal to decimal, the fact coming in from one completely oblique direction matches numerically to the decimal point from a different direction. We start to gel some ideas, and that's where conversations can start. Remember, none of these papers, none of these ideas are peer-reviewed or published. These are conversation starters. So regardless of a scaling factor with 1 times 10 to the negative 11 to drive a decimal point, what we need to focus in on is the fact that time changes at a rate of 6.6743 seconds for every second of clock time. And that number exactly matches our gravitational constant. That, for me, is a conversation point. Now we can use that relationship to reverse engineer Hubble constant, which we're going to do right now. Because from the temporal sciences perspective, the Hubble constant does not at all measure the rate of distance of change. It measures the rate at which time changes for distance. So it's drastically different. We've got distance, and then we've got rate of change of time. And so temporal sciences doesn't focus on distance, focus on rate of change of time. So let's continue on before I further confuse things. So we've got G, gravitational constant, equals the Hubble constant times current diameter of the universe divided by speed of light c times the scaling factor. Below, the next slide, we're going to do the equation work for that. Okay, we're going to solve for HO. We're going to rearrange that equation, pull HO out, rearrange the variables, and then substitute those variables with their generally accepted values that are listed on the screen right now. So we're going to carry those values forward. For distance, we've got 8.8 times 10 to the 26 meters. Speed of light, listed out here explicitly, just for reference. Gravitational constant, 6.67430 times 10 to the negative 11. We're all familiar with that. And then our scaling factor, where we're driving the decimal point and we're adding in some dimensions or manipulating dimensions. Because for our HO calculation, we'll actually be using the scaling factor to be pulling out those dimensions because they'll be in the denominator. We'll move to the next slide. Okay, so here we go. At the top here, we have the G equals HO D times scaling factor divided by C, just like we saw before in variable form. Now here, we've got numeric replacements. I left SF in there just because it's noise, and we'll keep it small with 2 letters. But we see HO standing out, the Hubble constant. And we've got the gravitational constant on the left. We rearrange the equation to solve for the Hubble constant, HO. HO is now on the left. On the numerator, we've got the gravitational constant times speed of light. On the bottom, we have the diameter of the universe, observable universe, generally agreed upon number, times our scaling factor. So we can pull out some dimensions and adjust the decimal place. Again, that's all we're moving is the decimal place. There's no number magic here. There's no changing of the mantissa or any numbers or anything. We're simply moving the decimal point. So we arrive at HO 2.274.07647, etc., times 10 to the negative 18, s to the negative 1 per second. We convert that to per second megaparsec. We've got 70.178 kilometers per second per megaparsec. So what does that mean? That means for that current diameter of our universe, which is continually changing, but for this general agreed upon estimate at some point in time, are 8.7987 times 10 to the 26 meters. For that specific diameter of our universe, we need a Hubble constant of 70.178 or converted 2.274, that Hubble constant needs to be at that exact number so that our gravitational constant remains intact. Why does this work out this way? Because our gravitational constant, there is no gravity. It is an effect of the rate of change of time. The Hubble constant is the rate of change of time. So if we remove distance from our line of thinking and reasoning and replace it with time, we can see with a little bit more clarity how they're part and parcel. Hubble constant is the rate at which time changes per distance, and gravity then is the result, or the word that shall never be spoken, the gravitational constant, gravity. The gravitational constant is the rate at which time changes. In total, 6.6 7430 seconds time goes by per clock second. That's our measured time. And so that time change is what drives our gravitational constant and our Hubble constant. They're bolted together, and they can't be separated out. So, therefore, that's it, 70.178 for our Hubble constant at our current diameter. So we'll move on to the next slide. We've got some variants here. So just for review, we have the I'm going to call it temporal Hubble constant to keep this speculative, unpeer-reviewed brainstorming from my end out of mainstream and really not overlap. I'm just going to call it you'll see a subscript T, temporal. It's a Hubble temporal is a gravitational constant times speed of light over any diameter. It doesn't have to be the current one. You choose the time, because through the time equation, you can pick your distance and get the time for the universe. And so you can just scale back and you can pick any time you want. So you can consider D a T. Like a calendar, you can move back and forth times the scaling factor. Again, we'll figure out the scaling factor, why that needs to be so brutal. I'll have to find some time and drive into that. Moving down, with C equals D over T, that's stated in document 1, foundations 1, definition of time. Let's see here. Yes, we'll substitute D with TC, and we'll plug that in the equation. So we've got Hubble, Temporal Sciences equals GC over TC times the scaling factor. We can make reductions, and then if we want to use, instead of the rate at which time changes, which is use of distance, we can go straight to time. And then we arrive at Hubble temporal equals gravitational constant over any time you choose. It can be right now. If you want to know the Hubble constant right now, you would put in our current cumulative measured time, because remember, time is the integral of clock time. So that measures the cumulative amount of clock time up until the point that you are interested in. Could be half the life of the universe or the current age of the universe. Whatever point you want to pick, you would plug in for T in the denominator. And again, that noisy scaling factor, yet to be researched. And that's it. And so that that Hubble has to always be in proportion and support our gravitational constant. I'll go to the next slide. Here is the Hubble temporal laid on a chart along with the lambda CDM, I believe, model or estimate. And you can see that they're pretty close. And you can see I've placed in here I've brought forward the distance version of the temporal Hubble constant. So gravity times speed of light over distance times a scaling factor. And so we've got distance there at the bottom. And on the left-hand side, we have HO values. It should have been H, or HT. But let's see here. And so that's it. We're getting a similar profile, taking a temporal route to define Hubble versus a distance route or temporal rate of change route to define Hubble, gives us a similar profile to the lambda CDM model. That I'm not that familiar with it, and apologies if that graph does not represent it. So there's that. In the lower left-hand portion of the plot, we'll notice a visual divergence between the two graphs, and we're gonna touch on that on the next slide. So for temporal sciences, the foundational idea is that the expansion for the universe is based on the rate of change of time. It's not distance. So the previous document with the gravity and the space-time really touches on that by just the complete replacement of G with its a temporal counterpart. And then we can start to really see how the rate of change of time it can actually impact things. Moving to the next slide here. This is the exact same plot we just saw. We see the temporal Hubble equation here, GC, D over scaling factor, or D time over D times scaling factor. But you'll see a new equation here. This is from document 1, time and distance, a new approach. This is the total differential for the rate of change in time. You'll notice that for the gravity and space-time document that I talked about and our work here today, we used the partial differential square root m square root e for d with respect to d only. So we've got a couple of more components I have not yet had time to unpack that can contribute to the rate of change in time. Up until now, I've considered them entropic. That positive, negative, they've balanced out because we did some exercise or an exercise on the age of the universe, that kind of thing, and used the rate of change with respect to distance to compute those numbers. As we did here today, we only used the rate of change with respect to distance for the Hubble constant analysis here today. I have yet to have the time to discover the changes in mass and the negative change in energy, since it's a denominator in the time equation, how that could impact things or the rate of change of time. Meaning, the reason I bring that up is because you notice in that graph, where I think it might be over there, that gap there, that's where we had major changes, transitions from energy to mass, mass to energy. And so there's more investigation on how the rate of change in time is affected from large changes in mass and energy and could address the gap in that chart or keep it the same. I'm not sure. Early days, early stages. Again, this is just conversation. Again, nothing here is fact, and this is just talk. In our world, distance is dangerous because it can hide things like the rate of change of time. So distance is dangerous. And for temporal sciences, time, specifically the rate at which time changes, is the key to unlock the door to hopefully many things. From what I'm noticing, if there's a distance problem out there, then temporal sciences can really possibly help to address that. So yes, time and distance, very exciting, very exciting. Let's see here. Okay. Well, that's it. What's next? Links to the documents are in the description below. Foundation documents served best if read in order. Otherwise, it's very confusing. The first one, time and distance, defines time, a new approach to time and distance. Universe framework for time and distance. You'll notice why I seem to hang on to square root m over square root e instead of just immediately right off the bat substituting or making substitutions, because we need those manual things. There's good information in there by letting mass and energy be front and center, and it's that visibility that helps to form the universe framework for time, distance, energy, and mass document, which is Foundations 2. Third one, time defines the gravitational constant, fundamental space-time curvature. We touched on that a little bit today. That document would be the third one to be read in the series, and that link to that is below. This theory and application exercise with the Hubble constant today, it would be attached to the third video. So when I do create the third video, that'll be Foundations 3, and this will be like 3.1, the video here today, because they're associated with each other. And so they can be organized that way. Please keep an open mind until you've read through the documents, especially to the end of the gravitational constant and space-time curvature document. It just gets very exciting when you come in from different directions and discover numbers that are very similar or the same that have been produced elsewise. And again, reminder, these are speculative ideas, unreviewed, unseen by any other human being. This is not truth. This is not fact. This is just nothing but conversation and sharing ideas. And that's it, offered as conversational starters. And well, I thank you so much. I thank you for your time, and we'll see you in the next video. All right, thank you.